So consider this one to be the beta angle. Opposite to beta is Fy, then sine beta is Fy over the hypotenuse, which is F, the magnitude of the force vector F. And we get that Fy equal F sine beta. This verifies. Let us start from the other side of the previous equation. Radical of x squared plus Fy squared. Substituting Fx by F cosine beta all squared plus Fy by F sine beta all squared. It is equal to, so the squared here is distributed to the F and the cosine. So as if we get F squared cosine squared beta plus F squared sine squared beta. Taking F squared as a common factor into cosine squared beta, not cosine beta squared, it's actually cosine squared beta plus sine squared beta, which is equal to radical F squared into, we know that cosine square of any angle plus sine squared of this angle is equal to 1. So here we have radical F squared into 1, which is radical F squared, yani it's equal to F. So the previous formula now is proven. This is the magnitude of the vector. Now find the resultant force on a particle using projection method. Consider a particle under the effect of two forces, F1 and F2 vectors. Use the projection method to find the magnitude of the resultant force Fr given the following figure. So given that F1 equal 18 Newton and F2 is 16 Newton in magnitude, we know, or we are given, that F1 vector forms an angle alpha with the x-axis and F2 vector forms an angle beta with the x-axis. We are given that the angle between F1 vector and the x-axis from the other side is, this is the obtuse angle. We are actually always interested in the acute angle between this force vector and the x-axis. So we know that a linear angle is 180 degrees. So then we can say that alpha is 180 minus 130, which is equal to 50 degrees. And similarly for beta, we're concerned with the acute angle, not the obtuse angle between the force vector and the x-axis. So here we're given that it's 160 degrees, then beta is 180 minus 160 degrees, which is 20 degrees. So now talking about F2, beta is 20 degrees. F2x, let us project it on the x-axis and y-axis in order to calculate the magnitude of its components. F2y is equal to, F2x is equal to F2 cosine beta, and F2 is given to be 6. So, and beta is 20 degrees calculated here, and we can do the calculations on the calculator, but please make sure when using cosine and sine, you have your calculator set on the degrees, not the radians, because here we are using the angle in 20 degrees, otherwise you're going to get wrong results. So F2x is equal to 5.64 Newton, and F2y is F2 sine beta. We are just applying the formula proven here. Similarly for F1, F1 is equal, now we have to consider the angle alpha not beta, because it's the angle between the force vector and the x-axis, and we do the calculations. As you can see, F1 cosine alpha is 8 cosine 50, and F1y is F1 sine alpha, which is 8 times sine 50. Now, to find the resultant force of these two forces, we have to sum the horizontal components on one side alone and the y components on the other side alone, because we cannot add a horizontal vector with a vertical one. So Frx, let us just check the projections that we did. As for F2, the x component is in the negative sense. And for F1, also the the x component is in the negative direction. This means that when adding up these, we have to write minus F1x minus F2x. Then the resultant force have its x component in the negative direction too. For the y component, let's check the y component. For F2, the y component is downwards. It's in the negative sense of the y direction, so we have to write minus F2y. However, as for F1, F1y is in the positive direction. So we write plus F1y minus F2y, and we get the result. Then Fr vector can be expressed in terms of its Fx and Fy, applying this formula that I mentioned.